Hey students, welcome to Sustainable Energy. I'm Rudi Schlaf, a professor at the Electrical Engineering Department at USF. This is part 2 of the Energy Basics segment. We will discuss energy exchange between objects through work and heat. We will learn why can heat only be exchanged with a colder object. Other topics will be efficiency of heat to work conversion and energy quality. In part 1 of this segment, we studied where energy is coming from, what types of potential energies there are. Part 2 of this segment focuses on putting energy to work. And so what you see here are two ancient steam engines. The first one by Newcomen. This was sort of the first engine that was useful for getting water out of coal shafts. And what you see here is a bucket, and so the way this works is fossil fuel is burned and water is evaporated, pressure builds up. We have two valves here around this piston. And so we open this valve and then the piston goes up. And then we close this valve, and now we cool down the cylinder with water, and that sucks the piston down, and so work is performed. Water is moved upwards. So this machine worked, however, it was very inefficient. And you can imagine the problem here really is that we need to heat the cylinder up in order to get the piston up, and then we have to cool the entire thing down, so remove all the heat that we can generate enough vacuum to get the piston down. So the great invention by James Watt was to add a condenser that was in a different location than the cylinder. And that would allow to do the cool down process in a different location, and so the cylinder could be kept at a high temperature. And because of that, the temperature difference between the high temperature reservoir and the low temperature reservoir, and we will learn in this part now what that means, this difference was enlarged compared to this situation. Therefore, the efficiency of Watt's steam engine was considerably higher than Newcomen's. And this higher efficiency essentially started the Industrial Revolution, because out of a sudden these steam engines became a viable proposition for all kinds of applications. We just saw that James Watt was able to increase the efficiency of the steam engine, and he achieved that by increasing the temperature differential between the hot and the cold reservoirs of his machine. So it's obvious that energy conversion efficiency is a very important factor in using energy. You saw this figure before. So what we're talking about is to use some potential energy, here symbolized by this Snickers bar, and then we're trying to convert it to useful work that allows us to transfer some of the energy of the Snickers bar onto another object. In this case, it was the shopping cart. And the efficiency is essentially the ratio between the work that we get out, or the transfer of some of that potential energy into kinetic energy of the shopping cart, relative to the amount of heat energy that is lost to the environment. In the case of a human, or also most gasoline engines, this is about a ratio of 1 to 3. So 3/4 of the energy is lost as heat in this conversion process from potential energy in the fuel to kinetic energy of the other object. The problem is that the heat that is lost to the environment is heat that is at a low temperature, right? It immediately assumes the temperature of the environment. And it is very difficult to recover any of this heat and restore it again into a more useful form of energy, such as in this Snicker bar. So in this part 2 of the Energy Basics segment, we will try to understand why we are losing heat and why it is virtually impossible to recover this heat. Only with a heat pump you can actually recover some of the heat of the low temperature heat that is emitted in this way. But this recovery again costs some energy, and so it is not possible to get 100% back of this energy that has been emitted into the environment. So in the end, we have a situation where we use high temperature energy, high grade energy, and we use it to perform work, and we always lose some of this energy as low grade heat at a low temperature, and we can essentially not recover 100% of this energy. That leads to a situation that we are constantly losing high quality energy, and life on Earth only exists because we have the sun that continuously pumps high quality energy into the system that we then can dissipate into low grade energy and thereby sustain life. So let's look into some energy basics. I said it already several times, energy is constant, and that is commonly known as the first law of thermodynamics, the energy conservation. In short, delta E equal 0. So we cannot make energy or destroy it. We can only exchange it between a system and its surroundings, or between two bodies. The only ways we can exchange energy is through heat and work. So why are we in trouble with energy? Availability of energy is not the issue because it's constant, so we should never run out of energy. But the problem is we need high quality energy that can be converted to useful work, like the Snickers bar on the previous slide. We cannot do anything with the low grade, low temperature heat that has been emitted to the environment. Another way to look at it, at least for heat engines, is that we want heat at high temperatures in desired locations, such as inside a combustion chamber, for example. It doesn't help us when the heat is distributed as a low temperature heat over a large area in the environment, because then, again, we cannot convert it to useful work. Okay, so when it comes to exchanging energy between two bodies or two systems, the only ways to do it is via work or heat. So here you have a systematic figure about that. We have a system so that contains bodies, and they interact with bodies on the outside the system boundary, via heat transfer and via work transfer. Whenever there is work transferred, there is always heat coming along in real systems. It is virtually impossible to build something where we can only transfer energy via work but have no heat transfer at the same time. However, when it comes to heat, it is entirely possible to do a transfer without any work. Just think of heating a house using fossil fuels. There we take the potential energy in the fuel, and then we burn the fuel and we release the energy as heat to the air and the house that is around the fuel. Some of you may have wondered why I talk about low temperature heat and high temperature heat. Typically the colloquial way of using the word heat is it's hot outside, water heat, especially in Florida. So we equate heat with a high temperature, but in a scientific context, heat is rather the total kinetic energy that we have in a body or in a gas. In other words, if we want to know how much heat is in a certain volume of material, in a body, in a gas, what we need to do is we need to measure the kinetic energy of all of the particles that are inside this body, and then add these energies up, and then we have the heat. So the heat is just the kinetic energy that is in a body, in an ensemble of particles. And this is used in the universal gas equation that you probably know. So here on the right side, we multiply the number of particles with the Boltzmann constant and the temperature. So the temperature really is proportional to the kinetic energy of the particles. Multiplying it with the Boltzmann constant transforms the temperature into an energy, and then we multiply with the number of particles, and we have the total energy that is in that ensemble of particles. Now this is equal to pressure times volume of this bunch of particles. And that makes sense because the volume at a certain pressure tells us how many particles we have. So the volume is proportional to the number of particles. And the pressure, that comes from
how hard these particles drum on the surface of the container that holds the gas. So that is the pressure. Pressure is nothing but an expression of the kinetic energy of the particles that are inside that vessel that holds the gas. So if we have a high pressure, that means we have a high kinetic energy in all of the particles, and then we multiply it with something that is proportional to the number of particles that we have. And so we end up with something that is equal to this over here, that is a sum over all the kinetic energy that we have inside the volume. So this is a macroscopic way to tell the energy, and this is a microscopic way to tell the energy. Here we just add up the energy of each of the particles. Here we look at some macroscopic observables that tell us the same. Now, if we have a certain amount of energy, Ke, in a system, we can achieve this amount of energy with few particles that have a high energy, a high temperature, or we can have the same amount of energy by using many more particles that are all at a lower temperature and thereby have a lower kinetic energy. So this means that two systems can have the same heat but strongly different temperatures. Right? Many particles at low temperature have the same heat like a few particles at a very high temperature. If we have two bodies that are in contact, after a while, they will have the same temperature. Everybody knows that, right? You put a cup of coffee on the table, and then after a while it cools down to room temperature. And so when that happens, the particles in the coffee and the particles in the room, they have the same average kinetic energy. And this state of affairs is called thermodynamic equilibrium. That means that essentially the same amount of energy over time is transferred from the environment to the coffee, and the coffee transfers then the same amount back to the environment, so that we have no net transfer between the two. So that is thermodynamic equilibrium. So let's summarize again. The important thing to take along here from this slide is that heat is not to be equated with temperature. Heat is the amount of kinetic energy that is in a system, but this amount of energy can be stored in many particles at low temperature or in fewer particles at a correspondingly higher temperature. So both systems can have the same energy but vastly different temperatures. Let's discuss energy exchange through heat a little bit more in detail now. As I just said, if you put a hot cup of coffee on the table and let it sit there for a while, it will cool down to room temperature. That means it will dissipate heat as long as it has a temperature that is higher than the temperature of the surrounding environment. It cannot go below this temperature. Right? It stops sending heat out to the environment once the temperature is the same. So we note here that heat transfer can only occur if a temperature difference exists. What we also see here is that heat transfer apparently only occurs from the hot object towards the colder object. So only if there is a temperature differential that goes downwards, then energy can be transferred from one body to another. We can only transfer heat from a hotter to a colder body. From this behavior, you see already that there are different qualities of energy. There is some very passive energy that is out there at a low temperature. It can't really do anything. It just lingers. While we have energy that is at a high temperature, and this energy is able to actually do something to the environment, to heat it up, to transfer energy from this object to the surrounding environment. Let's try to understand now why heat can only flow from a hot to a cold object. And that brings us to the question, how is heat actually exchanged? So remember, heat is just kinetic energy of the particles within the object. Therefore, in a hot object, the particles, the atoms, the molecules, they move rapidly. If it's a gas, they have a high velocity and they just bounce at the walls here and enjoy their kinetic energy. If it is a solid, then this is vibration. So the atoms, they just vibrate more vividly in a hot object than in a cold one. In a cold one, everything is pretty placid and there is little vibration, or the gas molecules move much more slowly. And so how is energy now exchanged between these two bodies? Well, it can only happen here at the interface. The particles on the hot side will bang into the wall towards the cold side. The particles on the hot side will bang into the particles on the cold side, and they will transfer some of their kinetic energy to the particles on the cold side. Now, the ones on the cold side, of course, also try their best. They also bang into this boundary, and they will also occasionally give some energy to the hotter particles, but it's easy to see that there is more kinetic energy transfer from the hot to the cold sides than from the cold to the hot side. In fact, there is a really nice classic experiment by Newton's cradle, that demonstrates that the faster particle always transfer energy to the slower particle when they run into each other and not the other way. Let's have a look. Here we go. This is a nice video that I found on YouTube. So what we will see now is the person will let the ball go, and you see it has potential energy. This is above these here, and so it will convert this potential energy into kinetic energy, and then it will hit ball number 2 and it will transfer all that kinetic energy to ball number 2. Ball number 2 will very briefly have that kinetic energy, then give it to ball number 3, and ball number 3 will convert it back to potential energy, and then the process goes again in the other direction. So the connection of this experiment to heat transfer is we can essentially envision the ball that has the energy as the hot particle, right? It will have a high kinetic energy down here, and ball number 2 is a cold particle at that sense. And this experiment essentially tells us that the hot particle is able to give all its energy to the cold particle, make it a hot particle essentially, and then this hot particle again can give its energy to the next cold particle, and so we get an exchange between hot particles and cold particles, but always from the hot particle to the cold particle. So let's see how this works. Okay, now we understand why hot particles give their energy to cold particles and not so much in the other direction. And so we have a situation like this here. A lot of heat will go from hot to cold, and colds can only transfer a little bit back to hot. Now this process, of course, will go on until the particles here have the same kinetic energy or velocity as the particles over here. And so we get a situation like this here, that they all have the same kinetic energy. And at that point, well, they will still bang into each other here at the boundary, and so we will exchange a little bit of heat from the right side to the left side, but we will at the same time transfer the same amount from the left to the right statistically. And so we get a little bit of heat transfer at the interface, but no net transfer. Both directions are equal. And so this is called thermodynamical equilibrium. Both sides have exactly the same kinetic energy distribution among their particles. Okay, now we know that heat transfer has a preferred direction. It only goes from hot to cold and not in the other direction. Now if we look at other processes that involve heat, they all seem to have a preferred direction. Here are two examples. One is passing a current through a resistor. So we're having electrical energy moving electrons through the resistor, and in the resistor we will dissipate some energy as heat, and so we heat up the environment. So this is a process that everybody knows works very well. However, if we would now heat up the environment to a higher temperature, we wouldn't expect a current to rise in this resistor as a consequence of that. Another example is the paddle wheel experiment. That's a famous experiment because it showed that heat is also an energy form, and that heat in this experiment is equivalent to the potential energy of the weight. So the experiment goes as follows. We let the weight go, and then the spool here starts rotating because the string unspools, and the paddle wheel turns, and then the viscous fluid in this box gets heated up because of friction. And in the end, we have an amount of heat in here that is proportional to the amount of potential energy that was converted. Now, it wouldn't be possible to reverse this process. Putting the equivalent amount of heat into the box wouldn't be able to lift up the weight back from the ground up to its start position. The reason for that is mainly that heat cannot give the molecules in the viscous fluid here a uniform direction of motion that would allow it to turn the paddle wheel to get the weight back up from the ground. All that heat accomplishes is that the molecules in here start moving faster, but everybody goes in random directions, and so we cannot translate this into a coordinated motion of the paddle wheel. So why are these processes that involve heat irreversible? Let's consider this simple experiment. We have a box that is full with cold particles on one side and hot particles on the other, and we have a wall in here that separates them. So what will happen once we pull this wall out? Well, for a very brief moment, there will be the red ones on this side and the blue ones on this side. But then, a split second later, we will be in a situation that is very close to this here. Because all these molecules move randomly. These are faster than these, but nonetheless, everybody moves randomly. They will distribute throughout the entire volume, and we will have a fairly homogeneous distribution of both types of molecules. So is it likely that these intermixed hot and cold particles will now decide that all the hot ones go on this side and all the cold ones go on the other? No, it's absolutely unlikely that this will happen. If we wait long enough, of course it could happen. If we sit there for 10 to the 40 years or so, there might be a millisecond in which we find all the hot particles over here and all the cold particles over there. But it's very, very unlikely that this happens. What's much more likely is that we're always in a state like this here. Sure, there might be imbalances that sometimes a few more red ones are here than on the other side and vice versa, but typically it will always be a situation like this here. Only very, very rarely this here might happen. And so this tells us a fundamental phenomenon in nature that systems, like these particles in this box, they go towards a more likely state. And since it's very unlikely that they go from a likely state back to a less likely state, then we can say we have an irreversible change of the state of the system. So we go from this situation to this one, but we cannot go back. This principle is expressed in the second law of thermodynamics that states entropy S always increases. In short, delta S larger than zero. And so for all our purposes, we can interpret the word entropy just as probability of the state of a system. So we always go from a less likely state to a more likely state of the system. So we just saw that all processes that involve heat are irreversible. Once the heat is gone, the energy is gone, and we cannot really do anything about getting it back. An interesting question is, are there reversible processes in nature? Now, if you look at a pendulum, of course in the pendulum we always transfer potential energy to kinetic energy and then back to potential energy. And so this can go on forever if we assume that there is no friction. And the big word here is assume. Because in nature, anything we do, there will always be some type of friction involved, and always there will be some heat dispensed to the environment. Even the best vacuum chamber you could run this pendulum in will still have a few molecules flying around that occasionally hit that bob, and it will slow down because of that. The only really reversible process in nature is heat transfer between systems in thermodynamical equilibrium. Only when two bodies have the same temperature, then we transfer energy from one side to the other and back, and it's completely reversible. Nothing changes, and of course that makes it entirely useless. So for all technological purposes, we will always have heat loss no matter what we do, and that will make these processes irreversible. So if we have heat, the question really is now, what can we do to extract useful work from this heat? How can we make the heat perform work on another body and transfer this heat energy to that body in a meaningful way, like push the car forward, raise an elevator from the ground, do all these things that we are so used to. So if we look here at the paddle wheel, the situation that we have inside the box, if we heat it up, if we just put the heat back that we got out of that weight drop, then all we achieve is that the particles are moving randomly around and they get a little bit faster. But the paddle wheel, of course, will be hit from all sides equally, and so will just vibrate a little bit, itself get hotter, in other words, but we will not be able to induce a motion. What we want is, of course, that these particles translate that kinetic energy that they get from the heat into a coordinated motion, that they all go in the same direction. But of course, you know that this is a very unlikely state of this system. And so by itself, it will never go from this condition into this condition. And this means we need to involve some technology in order to get the particles in this paddle wheel to move in a coordinated fashion so that it starts rotating. We understand now if we want to use heat to perform useful work, we need to find a way to corral the random motion of all the particles in the heat-containing medium into a collective motion of a macroscopic object, which is the body into which that heat energy is being transferred. The classic way to do this is with a piston. Here is a schematic depiction of a two-cycle steam engine. We have a pressurized steam inlet in the center and we have two exhaust pipes. So in the first cycle the steam comes in here, the valve is now in the left position. That means the steam enters the left chamber. It then pushes the piston over to the right side, because this here is at atmospheric pressure at this point. The exhaust pipe is open. Then in the next cycle the valve shifts over. There is a feedback mechanism from the flywheel that pushes the valve over in the right moment. Now the steam enters this right side of the piston and thereby pushes it over to the left side. The achievement here is that the chaotic random motion of the gas under pressure is being channeled into the movement of this piston to the left or to the right. So we transfer energy from the heat that is in this gas to kinetic energy that is in this flywheel with this process. Let's examine what happens with respect to energy transfer in such a piston-based system. Let's consider this model experiment. Of course, this is not a very practical engine, but it's interesting to look what's happening here. So we have this cylinder. It's filled with a gas under the load, and the load sits here on these two blocks in its initial position. And for a moment now, imagine that there's also a pin stuck in here that holds the load in place, so it cannot move no matter what the pressure is in here. And now we bring the cylinder in contact with a reservoir. That could be a boiling pot of water at 100 centigrade. And so we let the gas now equilibrate with this reservoir, so we have 100 centigrades in here. And let's say we put in 100 kilojoules that way. So the gas increases its energy, it is now at 100 centigrades. And of course, if you remember the gas equation, because the temperature is higher, we have a higher pressure. Okay, so now we remove the reservoir, so here no more energy is being put into the gas. And then we pull the pin out and we let the load go to its final position up here at this second set of blocks. So the force applied by the gas pushed the load up this distance. So we can calculate here the work that was performed on the load is the force times the distance the object was moved. And so obviously we transferred some energy into this load, which is now potential energy because it is a little bit higher up. Now what happened in the gas? Well, because we allowed it to expand and push the load up, some of the energy in the gas must have been transferred to the load. And it's obvious we performed work on the load, And so some energy must have gone from the gas now into the load, which has here a higher potential energy. And indeed, if you would take a measurement, the gas now has a lower temperature, let's say 90 centigrades. So it went from 100 centigrades to 90 and the load is higher up. So what happened now to the heat energy that we put in the beginning? Well, two things. The load is up higher, that's pretty obvious, but also the gas is hot. And the temperature of the gas, the heat that we put into the gas with the goal to move the load up, this energy must be considered a loss. Our goal was to move the load, not to heat the gas. The gas is just the medium that allows us to transfer heat energy into linear motion and finally potential energy of this load. Furthermore, the gas now has a lower temperature than the reservoir from which we took the heat in the first place. And you understand now, because this is a lower temperature, we cannot get this energy, no matter what we do, back into the reservoir. And so really this energy can only be considered lost. Maybe we could use it to heat a house or something. 90 degrees might be good for that. But in this engine, for the purpose of moving the load up, this energy in the gas is lost. Let's take this a step further and run this engine repeatedly. So the purpose now is to put a load onto the higher level and then return the machine to its original position, put another load on here, move it up, and so forth. So do it repetitively, like practically all engines. So we put in the energy, we heat the gas, the load moves up, the gas is hot, we take the load off. Now we return the engine to its starting position, and of course, because the gas here is at high temperature and has pressure built up that keeps the piston up, we have to now cool down the gas in order to be able to move that piston back down in its starting position so we can put the next load on there. And that means we have to remove the heat from this gas and dump it into a reservoir at a lower temperature. And this is really unfortunate. We can only get the heat out of this gas by letting it equilibrate with a reservoir that has a lower temperature. What we achieved here is that we took high temperature energy and we converted it into low temperature energy. And we know now that this low temperature energy is useless. We cannot generate high temperature heat energy out of this. This energy is just lost. So in this very inefficient engine, we only converted 15% of the energy that we put in from the high temperature reservoir into mechanical work, and 85% went as low grade heat into the low temperature reservoir. This is the working principle of practically all heat-based engines that we are using. If you think of this as a gasoline engine, then the low temperature reservoir, that would be the air that is going through the radiator, and the high temperature reservoir, that would be the heated gas after the explosion in the combustion chamber. The work that's being performed by the gas in the case of a car, that is of course imparting kinetic energy on the car. So now you understand why it gets pretty hot under the hood of a car, because we have to get rid of all this energy during each of the cycles of the engine. This here shows a schematic of a coal-fired power plant. There's a boiler that needs to be heated so we can turn water into steam and build up pressure. The coal is being burnt and heat is generated, and that heat is making steam. This steam now performs work in a turbine, which is connected to a generator that generates electricity. And after the turbine, the steam needs to be liquefied in a condenser, so we get a pressure differential between steam in and steam out that makes the turbine spin. In the condenser, we dump the heat out into the low temperature reservoir, which is typically a river or these big cooling towers that you see next to these type of plants. Okay, so here we have now liquid water again, and this water is then pumped back into the boiler, and there we heat it up and then steam drives the turbine. So this is the cycle of the working fluid. The pump here stands for all these things that consume energy in a coal-fired power plant or in any power plant. Pumps, conveyor belts, light, all that stuff. So that further reduces, of course, the efficiency of this process. Let's summarize. In all heat engines, we have a hot source and we have a cold sink, hot reservoir, cold reservoir. We put heat at a high temperature into the engine. Some work is performed and some of the heat is being dumped into the cold sink because we have to restore the working fluid to its original condition for every cycle. Some of the work falls victim to systemic losses, which further reduces the efficiency of such a heat engine. Let's see what determines the efficiency of a heat engine. So efficiency here means how much of the heat that we put into the at the high temperature reservoir into the process is actually being converted to work, and how much of that energy is going into the low temperature reservoir. Now, if we just consider the heat that comes in and the work that goes out, the efficiency is just the ratio between work out and energy in on the hot end. Since the work is just the difference between the energy, the heat energy that we put in and the heat energy that we dispense into the low temperature reservoir, we can write the efficiency is equal to Q high minus Q low divided by Q high. And so this here we can transform into 1 minus Q low divided by Q high. And so you see that the efficiency gets closer to 1 when Q low is small and Q high is high. We put in a lot of energy up here and we only put out very little energy into the low temperature reservoir, and that means we would get a high amount of work out of this process. The efficiency would be high. So how can we achieve this? That we put in a lot of energy up here and when we take little energy out down here? Well, we need to make Q low small and Q high large. Now Q, the heat energy that we put into the system, is just NKT. We saw that in the gas equation. So it's the number of molecules that we're heating up times the Boltzmann constant and then times the temperature. So this and this is constant, so the only thing we can change is the temperature. And that of course means we need to make the temperature up here as high as possible and the temperature down here as low as possible. When James Watt improved the steam engine, his breakthrough was to make this low temperature reservoir lower. So he essentially managed to bring it down to the temperature of the environment by putting the condenser away from the hot piston and the hot cylinder of the steam engine. Now, it's difficult to go lower with the temperature because the environment is all we have to dump out the energy out of the heat engine. Sometimes one can find a cold river or so this allows to change the temperature by a few degrees, but essentially we're stuck with the environment here. Therefore, the typical way these days to increase the efficiency of a heat engine is by rising the temperature of the high temperature reservoir. And so there are now steam plants that have superheated steam and so forth, and so the best plants that are being built these days have about 60% conversion efficiency. Here in this table you see the relationship between the temperature differential relative to room temperature, assuming we have a perfect steam engine. So this is the theoretical maximum that we can achieve with these temperature differences. And so you see here, if we go from 925 Kelvin to 303 Kelvin, we would get an efficiency of 67.2%. Of course, this is a theoretical value. Real steam engines, of course, have friction and they have those pumps and all these things that eat energy. So this number typically is considerably smaller than the theoretical limit. After this consideration, it is clear that there are different qualities of energy. And so we can say that energy or heat that has a high temperature is a high quality energy, while If we have low temperature heat, then this is low quality energy because we cannot perform work with it very efficiently. The dependency of efficiency on the temperature differential also immediately points to a fundamental weakness of geothermal and solar thermal energy conversion schemes. In the geothermal case, for example, since temperatures are rarely higher than 300 centigrades, the efficiencies are usually below 10%. This suggests that geothermal energy is usually best used for direct heating applications like heating houses. In the case of solar thermal energy, concentration is usually used to achieve higher temperatures. That enables solar thermal power plants that have a relatively high efficiency. And here we are back at our energy flow diagram. I hope you understand now that we have to have this big amount of lost energy. This is the energy that all these heat engines that we're using to convert the potential energy inputs to work, that they dump into the cold sink. So we're producing with all these inputs, pretty much all of them, we're making a hot reservoir, and then we're using heat engines to make work that propels our cars and planes and industrial machines and whatever. And in this process, we have to put up with this energy loss to the cold sink. And you know now that this energy is really lost. We cannot really do anything with it because it has a low temperature. Some more comments about energy quality. You know now that heat energy, the quality factor basically depends on the temperature. The higher the temperature, the higher the quality of heat energy, because we get a higher efficiency out of heat engines when we convert part of that heat to work. In terms of energy quality, it is probably easy to come to the conclusion that electrostatic potential energy is probably the highest quality energy available. It's also the most versatile form of energy. If you consider, for example, conversion to mechanical work, an electrical motor can reach efficiencies that exceed 96%. So it would only lose 4% of the energy to heat in such a motor. The problem really is to come up with that electrostatic potential energy. If we do it in a regular power plant, coal-fired or gas-fired, then you know now we lose a large part of that fossil energy, of that fossil fuel that we put in there to heat. If we use light in solar cells, if we use photons, they can of course be directly converted to electrostatic potential energy, and so this can be very efficient. However, since we have a distribution of wavelengths in these photons, and we will discuss that in the solar energy segment, we also have a lot of thermodynamic losses. So solar cells are really not that efficient typically. If we utilize kinetic energy that is available to us, wind comes to mind. That can, of course, also be converted to electrostatic potential energy with high efficiency. Generators can reach 95%. However, it is difficult to get all the energy out of the wind, or it's rather impossible to get all the energy out of the wind because the wind has to keep moving as it goes through the wind turbines. Therefore, we cannot extract all of the kinetic energy that is in the wind. So the main problem with electrostatic potential energy is really to make it in the first place. Other challenges with electrostatic potential energy are transport and storage. When it comes to transport, the high voltage lines that we're currently using, they have easily a loss of 10% or so until the energy reaches the end user. When it comes to storage, well, there isn't really much on a large grid level scale. The only thing that we have right now is hydro storage, and that is less than 1% of the grid capacity. Batteries, on the other hand, they have the issue that they have a very low energy density per weight. Even the lithium-ion battery, which is considered the pinnacle of technology right now with batteries, has 1% of the energy density of gasoline. That is the main reason that it is so difficult to give electrical cars a useful range. And this brings us to the summary of this segment. I hope you understand now that all the energy that we're using goes back to potential energy stored in atoms, gravitational, electrostatic, and nuclear potential energies. Even wind, if you think of it, is the result of the fusion process in the sun that converts binding energies in nucleons, and that energy then heats the atmosphere and creates kinetic energy that we can then use as wind. Even the best heat engines waste energy to the environment. That is a consequence of that need to expel low temperature heat into the low temperature reservoir. That lowers the quality of that heat energy and makes it less useful. So in the end, we always end up with low grade energy that is just distributed in the environment. In fact, all technological processes waste energy that way. Everything we do produces heat, and so there's only one direction of this process, more and more low grade heat that cannot be recovered. So it's obvious that this system can only work if we have a continuous, perpetual high temperature reservoir from which we can draw high quality heat to generate useful work. And of course, on Earth, what we have is the sun. That is the perpetual high temperature reservoir that makes everything possible that we see around us.
This concludes part 2 of the Energy Basics segment. Thanks for watching.